Okay, so my name is James Richings. I am the current convener for the ARCHER2 webinars, and today we have a series of 3 talks looking at the science behind the image competition we run every year. So today Dale, Shi and Jan have offered to present a little bit more information around the images and videos they submitted, and to try and sort of discuss how they've done a bit of visualization and why the submissions are so interesting. So to start with, we will have Dale Hughes from Queen's University Belfast looking at his submission on acetylene molecules subject to intense ultra-fast laser pulses and the time evolution of the electron probability. So Dale, when you're ready, could you share your presentation, please?
Okay, so I'm just going to leave this up for now to begin with. Okay, so I'll just pick a still here from a shot. So this is this is actually slightly different from the image I originally submitted. This is a H2O molecule. The original one was acetylene. There's visualizations for all these. So fundamentally, what these are time-dependent density functional theory calculations. The output of which is then represented using basically quite a simple Python script that can plot the charge density. So what this is representing is if you were to be able to see a molecule, which you kind of can't do because of issues with the wavelength of light and whatever else, if you could somehow see the charge density around a molecule as it evolves over time, this is what you would see. And we look at situations that are example after a laser interaction with a molecule or a charged particle interaction. Basically, we put molecules in situations where they are quite far out of equilibrium and where we can see interesting processes happen. I should say I'm a PhD student at the moment at Queen's University Belfast, working with my supervisor Dan Dundas, and we're using to do these TDDFT simulations. We're using a code called Edamame. And Edamame has got this, like many other TDDFT codes, it's got the ability to output the charge density over time. So building on that, we basically were able to build quite a simple Python script, just use matplotlib really to plot the charge density at each time step of the simulation. A little bit of playing around to get a nice something that worked nice graphically. That was kind of important too. And there are a lot of frames, there's a lot of processing that's done, a lot of files that need to be processed after one of these simulations. So the visualization script that we've got actually is parallelized using MPI, so that also takes advantage quite well of the capabilities of ARCHER2. So I'll just show the evolution of this system over time so we get a little bit of an idea. You'll see basically the time in femtoseconds in the bottom left corner. That it shows you how short a time that these processes happen over. And this is after what you would call a kick to the molecule. So this is, instead of giving a realistic a realistic laser pulse, a realistic irradiation from some of the process, this is where we simply provide a kick to the molecule in the form of a simple step potential. So I'll allow this to play now. Hopefully everyone can see this. So what you're seeing here is, yeah, there's a little bit of stuff going around the outside of the molecule here. This is some spurious charge density that you only see because of boundary conditions of the box. I thought this looked kind of great though, and shows off the plotting capabilities. And in the center of the screen, you see the oscillating charge around a H2O molecule. And I don't think it will come across so well over streaming like this, but there is also sound with this video that represents the dipole moment. So you're actually able to hear this oscillation take place. And what I will do is I will make a zip file with all these movies that I'll show and upload it later on. If anyone wants to see the actual full video, they can. So that is with sound. So that's a decent one there. I'll show another one here. Oh, not that one. So where are we? Yeah. So this is the one that was featured in the image competition. This is an acetylene molecule after it's been struck by a laser pulse. So a laser pulse is coming in and is moving polarized in the left to right direction, left to right direction, that is. And yeah, you'll see the charge density of the system evolve over time. Again, the time is in the bottom corner. And this produces a particularly pretty pattern, I think. You can see that we have, in this case, absorbing boundary conditions around the edge of the simulation box, and they are, yeah, they provide a more realistic setting for the molecule to be existing in. So it's also visible here that there is a change in behavior quite long after the laser pulse has ended. Basically, we're in a slightly different regime of vibration now, where it's much more chaotic. Originally, it started off quite symmetrical. If I were to roll this back, you'll see the really nice symmetry to this. Around 300 or 400 femtoseconds, that's gone, and we end up with something much more chaotic. That's a process that we call dipole instability that we're actually investigating at the moment now. So just to recap, this is the product of a time-dependent density functional theory calculation, real-time TD-DFT, you would say. This allows you to some degree of approximation, represent the evolution of a quantum system over time, and the technology is really moving on leaps and bounds with this. And a fairly simple plotting script was used, basically written in Python, using mostly Matplotlib, parallelized with MPI, and it could be run very well on the ARCHER2 system. So I think that's probably the bulk of what I would like to say. As I say, I will upload these videos into a zip file if anyone wants to see this afterwards. They are a lot better whenever you see them in full quality, as in on your local machine, and even better if you can access the sound that's in them. So all the videos have sound that comes from the dipole moment, also output from the simulation. So yeah, I'll maybe finish off there if everybody's happy with that.
Thank you very much. Does anyone have any questions? I think everyone's okay just to unmute their mic, Claire, if I'm correct. Ask.
Mm-hmm. Okay.
If there's no one jumping in, I will ask one myself. So you're pushing these out of equilibrium with some pulse, and then you're seeing a ring down. Is that why the intensity is dropping? I suppose that would be represented in the sound intensity decreasing as the sort of simulation.
Yeah, actually, that's an interesting problem with it. So the level of approximation we use at the minute is TD-DFT with the local density approximation. So if you know a little bit about DFT or TD-DFT, it's an approximate method to the extent that there is an approximation used for the exchange correlation functional. In other words, the energy of a certain charge density is assigned by a Hamiltonian, and one of the terms in the Hamiltonian is approximated. So given that approximation, there actually is no dissipation yet. If we were to just run that simulation on forever, you would actually see the molecule continuing to vibrate forever. At the moment, we're working with another team, ARCHER2's team in Toulouse, to implement a new technique that basically involving an ensemble of TD-DFT simulations with a stochastic element in there that will allow us to accurately calculate the dissipation over time. So you would see it cancelling down to zero motion eventually. For now, there's no dissipation, so you'll actually see that ringing on forever, and any kind of dissipative effect isn't included in those movies yet. Yeah, I saw another question there about the parallelization method. Yeah, it is MPI for pi. Basically, you ask for, say, however many nodes, even 128 cores would be quite reasonable to do one of these videos. You have a kind of Python script that we just run on a single core that launches, well, initializes any variables you want. So say, the parameters for matplotlib, things like that there, processes the audio, and at the end of that, it will spawn, say, 128 processes that will, to basically do the rendering process. It's what you would call embarrassingly parallel, in the sense that there's no communication between the cores. It's not really required for this. Any communication is done in a very basically done at the beginning. It doesn't have to be. The cores don't have to communicate with each other as they would if it was, say, a numerical simulation. So you could implement this just as well with a much more simple method, maybe OpenMP, or in Python, one very useful tool is just the multiprocessing module that you can load. It would make it very straightforward to render a lot of any in inverted commas embarrassingly parallel task can be done very well that way. But it was interesting basically to implement this with MPI in the sense that it would be useful training for slightly more advanced projects down the line. So it also means, to be fair, it does mean that it's very usable on say a very large number of cores. If you had a really long video and you wanted to do it over 1,000 cores or something like that, there you could. So yeah, hopefully that clarifies that. Thanks.
Okay, if there's no other questions, I think we'll move to our next presenter. Thank you again very much, Dale.
Brilliant. No, thanks so much, James. Thank you, Claire. I'm looking forward to the rest. The images that I've seen so far for the other guys look fantastic too. Thanks.
Okay, next, if we have Chi. Fantastic.
Okay, so I can kick off. So my name is Chi Zhou, and I'm a postdoc researcher from the University of Edinburgh. Today I'm going to present our work on the mesoscopic modeling of cell-scan hemodynamics. This is a work carried together with Miguel Bonabeth and Tim Kruger at the same university, and also collaborators from the University of Manchester, Eleanor, Oliver, and Igor. So essentially, we focus on this kind of a cellular blood flow simulations in the intervillous space of human placenta, which I will be explaining a little bit more. We use the open source software HemLB, which is a very large-scale, highly paralleled flow solver combined with immersed boundary for particulate simulations. So over these years, we have been developing an in silico framework for this kind of like a microvascular blood flow. Either is for in vitro or in vivo comparison with microfluidic experiments or animal data the biologists they obtained for us. Essentially, we have been looking at this kind of like red blood cell dynamics in low Reynolds number microchannel flow, and also we look at this red blood cell distribution in biomimetic artificial vascular networks, and we further, proceeded with realistic animal model vasculature from the mouse retina, for example. So to look at the traffic, the mechanical transduction process between the red blood cell traffic and the development process of the vasculature. And recently, we have been looking at this kind of canonical disordered porous media in preparation for the talk I'm going to give today, which is the simulation of human placenta tissue. So essentially, human placenta is a very important organ developed during pregnancy. It's the interface between the fetus and the mother, because we know that the fetus grows like within the uterus of the mother and is embedded in a watery environment, and it needs something to primarily oxygen and nutrient. We know, during pandemic, we know how important our lungs are for us. Again, like that's re-emphasizing the importance of this kind of like oxygen transport exchange of gases between human beings and environment. And for the fetus, the only pathway for him or her to do is like through the mother, the placenta interface. So if we look into the microstructure of the maternal fetal interface, it's very complicated. Essentially, you have the spiral artery from the mother to inject maternal blood, which is rich in oxygen, into this placenta interface. Then the fetal blood is like is transported through the umbilical cord, as we can show from the last slide, and then it meets with the maternal blood in the placenta, but they're not in direct contact. They need to finish this kind of like transport exchange process through this kind of very delicate pore throat geometries. Essentially, the vasculature of the fetus is like a tree root-like structure. It's like if you think of the roots of the tree, it penetrates into the placenta. Then the maternal blood is like surrounding the tree roots. We call it villi structure to finish this kind of a flow mediated diffusion process. And if we construct this kind of like tissue structure, we see it's highly porous, and we can see like it can be represented by this kind of pore and stick model. In pathology, like usually this kind of structure changes. It either become too dense or it become too dilute, and also there is this kind of issue of tissue alignment. But it's unclear how structural alterations are associated with this kind of functional disorders of the placenta. This question is very important because there are currently around 10% of disorders, placenta disorders, that can be associated with the preterm or stillbirth, which is a large issue. So we kind of want to get some knowledge from this kind of like structural features to predict the potential like fatal disorders in the mother based on some preliminary imaging. So the way how we do it is like essentially we extract this kind of like imaging signals, and we reconstruct this three-dimensional flow domain. Then we simulate the red blood cells, how they flow within this domain to extract the fluid dynamics and also the cell transport information. In the future, we also need to incorporate this oxygen transport model on top of it. So essentially look at the advection diffusion process. So the outlook for us is like, first, we want to generate some constitutive laws or for reduced order models, because essentially we don't want to get stuck in this kind of like tissue volume simulations. We want to upscale our simulation to organ level or to even larger scales. And also we, as I just mentioned, we're going to incorporate some advanced transport models for tissue oxygenation and the solution exchange purposes. Essentially, we want a coupled maternal and fetal blood flow in the end, because I talked about this kind of like separate blood circulations, the fetal blood and the maternal blood. In the end, we want to couple them to see how this kind of like interfaced phenomenon can infer about the potential placenta disorders or pregnancy complications. So with this, I would like to acknowledge our model, our project, and novel models for hemodynamics and transporting complex media in collaboration with the University of Manchester, and also UK Commerce for our access to ARCHER2, which is super useful and necessary for our project. In the end, I would like to thank the FemaleB development team, and thanks a lot for James and Claire for inviting me here. It's very quite a pleasure for me to present here. Thanks a lot.
Thank you very much. Are there any questions in the chat? If not, I have one at least. Okay, there's nothing there right now. So for the, I think it was your second to last slide, or one before,
yeah,
slide number 5, you have the image which you submitted, I think, or a variation of it. Is that which, so the sort of the ghost or the very sort of light gray structures here, that's what's being kind of presented on the slide above? Sorry, on the image above. Is that the normal case, the pathology, or one of the pathologies?
A second, please. I go to, you mean this slide, right?
No, I mean the slide that you were just on slide 5.
Okay. Second, please. I think it's giving me some issue changing this one, right? Slide number 5.
Yeah. So the bottom left image is the one you submitted for the image competition.
Yes.
And the structures, I assume, is sort of the sort of slightly transparent section. That's the tissue structure, and the red dots, which is the blood cells flowing through this. The pathology, your two pathologies above, and the normal case. How do you link those two?
Yeah, this case I actually currently is from the previous tissue samples we have, and we are we cannot determine whether it was from a patient or actually from a healthy pregnant a woman. So, but in the future, in other simulations, we have this kind of a categorization to make sure we can reflect this blood flow. But indeed, you are true. You are correct about this. Tissue segmentation, but note that the tissue we're referring to usually is belongs to the fetal side. So the blood flow, the red blood cells are actually flowing between, in the cavities of this kind of vasculature is flowing between. It's like going through a sponge, something like that.
Thanks. I think we have one question that happened there. So, which software are you using to render these images in 3D? Because it seems that the image of the volume is multidimensional.
Oh, it's that we actually use a machine learning algorithms. It's called UNet. We do the 3D rendering. Essentially, you have this kind of image stacks for a 3D volume, so you can reconstruct this kind of image based on the machine learning generated image signals.
Okay, so we have another question from Alexei. Why do the fetal and mother blood flow simulations need to be coupled? Can they be simulated in a single simulation?
Yeah, that's very, very interesting question. Actually, because already for the single domain simulation is very complicated because you will have different boundary conditions, and also the flow, flow rate, and also the hematocrit. Hematocrit means the volume fraction of the red blood cells that are very different at the fetal side, the fetal side and the maternal side. So essentially, you have two different flow circulation systems. Currently, it's too expensive, and also we have no clear idea of what happens at the interface. We need advanced models essentially to bridge these two models together without interfering their own functioning. That's why we need a coupled model in the future.
Thank you very much.
Yeah, thank you. Thanks for the next question.
Okay, I think that's all the questions I can see in chat. I think we'll move on to our next speaker now, if that's okay. Thank you again for the lovely talk.
Yeah, thanks a lot.
Okay. And next we have Shan Fang from Darsby Lab at STFC.
Hello.
I can hear you, yes?
My screen.
Yes, please.
Okay, I'll start. So my research is about the hypersonic vehicles. So the typical hypersonic air-breathing vehicles look like that. The flow coming in from intake and combustion happening in the combustion chamber and the ejection from the nozzle. So the combustion is look much simpler than the normal combustion in our cars and the turbojet, because and such a high speed flows, any complex geometry will lead to the massive loss and drag. So we use simple cavity, and the cavity generates the shear layer. For this one, we see the strong turbulence fluctuations over the shear layer, and because the shear layer imping on the tilt wall and it generates compression wave. The compression wave becomes shock waves, and the shock waves reflected between the upper and the bottom walls, and leading to the interaction between the turbulent vertical structures and the shock waves. So this is the thing we show in the video, because but furthermore we did the further research. So in principle, we want this cavity named flame holder can create like the stable high temperature environment, so that the ignition can happen here, and within the short distance there will be the heat can be released into the combustor, so there will be energy be input, and the thrust will be generated. So follow that follow the research shown in the video. We carry on the research with the case with the chemical reaction on, so basically the combustion. So for this we can say when the high temperature in the shear layer triggered the ignite the flow. So we see that this is a heat release rate. So large amount of heat being released on the side of this flame front, and around the platform in the boundary layer, we see very high temperature flows. That is the result of the ejection of the fuel and the combustion. And for that case, we can see even more complicated flow. We see the interaction between the shock wave, the turbulent structures, and the flame front. So using this high fidelity direct numerical simulation approach, we are able to get the detailed flow structures and the complex physics of the shock wave, the flame front, and the turbulence, and we can study the interaction between these nonlinear flow phenomena. That will give us the deeper understanding of the flow physics inside the supersonic combustor, the supersonic combustion ramjet, scramjet. So that will help the engineer and the science to design the high performance scramjet to power the future hypersonic vehicles. Oh, that's basically. I'm not sure if I make myself understood.
That was great. Thank you very much. I certainly have a couple of questions, but does anyone in chat have anything they'd like to ask first? Okay, well, while you're thinking, I'll just ask.
Yeah, actually, yeah, I have one question for Jianfang.
Yes.
Jianfang, actually, I watched your video. I was really amazed by this. It's cool. It's like a film trailer. Like, actually, do you need to use like ParaView in multimodal like mode to actually to parallelize your visualization process, because it seems very expensive, right?
Yeah, I use like the server custom mod. So on Archer you actually use ParaView and use Archer as a server, and so you don't need to transfer your data to local, and you can operate. You can submit the post-processing script and do you set up all the cameras angles and the scenes you want to show, and you leave the machine. You run the job script for a night. You get all the pictures and you glue them into a video. The very efficient way, I would say.
Yeah, thanks a lot. Hey, that's my thought. Like you will probably using ARCHER2 like rather than local server to do that. Yeah, cheers. Yeah. Thank you so much. Cool research.
Cheers.
So Dale asks, have you considered adding sound to the simulation video by sampling the air pressure at a given point?
The sound effect.
Yes. So
yes, we do.
But inside a scramjet.
Yeah, I did actually. If you hear carefully for this one, there's a sound effect of the like a blast wave and the flow being like the sound of the flame, but it's all fake. I added the sound effect, but it's not actually from the simulation result, the pressure waves. No, but it's give the idea like the flame.
But could you use some of the data from the simulation to add sound directly? Or would it just?
You mean extract the acoustic waves?
Yeah.
Yes, in principle, yes. But for your information, this simulation is very, very short. It's like only like 1 to 2 microseconds. So it will be very, very short sound if you in physical world.
Yeah.
Because the flow speed is so high, and the geometry is not very big enough. So the actually passing through time is very short. Yeah, but it's good. A good suggestion. I have thought about that.
Great.
Thank you.
One question I had was around in traditional jet engines, or you were used to sort of military jet engine. You used to the idea of shock diamonds being presented on the external flow of a turbojet. If you have this sort of triangular pattern in your simulation. Is that the equivalent shock wave?
You mean with the turbojet, the diamond-shaped shock waves?
Exactly. Yeah.
I'll say it's a different things, because the diamond shock wave is because when the jet is to the atmosphere, there's an unbalance between the pressure, so the shock will be bouncing back, a force and back between the edge of the jet and the atmosphere. But for this one, the shock wave is being bouncing back between the two walls, so it will be a bit different, but aerodynamically they have some similarities.
And is there a particular shape that you look for that would be deemed to be this be an efficient engine versus an inefficient engine in these shockwaves? Would you like to see more elongated deflect, like the distance between the reflections off the surfaces be longer or shorter?
Oh, that's a very good question. So I think the principle for design the combustion, you don't want the shock wave to largely disturb the flow to cause a fluid separation to leading to a very large loss. So we actually published this result on the physical fluids recently. So we analyzed the loss. So this turns out, and this Mach number and the Reynolds number, the loss caused by shock wave is quite minimal. So what I would say for this configuration, the detailed position of the shock wave, it does not really that matters. But for the selector of the geometry, I think it's another question. We didn't choose any geometry tested in the experiment. So we kind of developed this like a standard model, but to our knowledge, the fluid physics inside is quite similar with some like the real combustion, real scram jet observed in the experiment. And our research partner, they're going to design the experiment with this configuration. So we're really looking forward to see the result in the future.
Excellent. Thank you very much. I don't see any additional questions in chat, or unless there was someone there. Okay, I'll just take the moment to thank everyone who spoke today again. That was really interesting to see 3 very different topics be presented in the same talk on a variety of areas and how different techniques have been used. But just to remind everyone, we have another one of these sessions in 2 weeks' time with 3 more talks related to the image competition from the end of last year. And we hope to see you there to see some more presentations. So thank you very much.
Thank you. Bye.
Thanks a lot.
Thanks a lot. This was actually really interesting. Really enjoyed this.